Okay, so let's say you were standing right here between a campfire and an iceberg. Never mind the ocean, don't worry about that. So if I asked you where you were feeling energy, you would say that you totally feel energy coming from the campfire. You can absolutely feel it. And you would say, no, not so much. I'm not getting any energy from this iceberg at all. Well, what's happening is since there's so much more concentrated heat in this place, the net energy flow is from the fire toward the iceberg. And as a human, you're just like, oh yeah, I can feel the heat coming from the fire, and there's nothing coming from the iceberg. But let me give you another example, a different example, and let's see how you deal with that. Let's say you've got a chunk of ice, and it's at 0 degrees Celsius. And let's say you've got another chunk of ice, and it's at negative 40 degrees Celsius, let's say. So if we put these two chunks of ice in a box, and if these two chunks of ice could talk, what would they say? Well, this chunk of ice would say, my goodness, I can feel all kinds of heat coming from that chunk of ice. Why? Because there's such a big temperature difference. So even though we humans look at this iceberg and say, no, there's no energy coming off that, there actually is energy coming from ice. And as it was told to me by a professor, anything that has a temperature radiates energy. So our concept of hot and cold notwithstanding, anything that has a temperature gives off energy, period. If you'd like to argue about that or discuss, we could stop the video for a second and maybe talk as a class for a minute. So the point of this video is to talk about the amount of power, or the number of watts coming off of different objects, whatever their temperature is. And so I made myself a list over here on the left of the things that matter. The temperature matters, of course. The hotter something is, the more energy it's going to give off. The size of it, its surface area matters. That should kind of make sense to you. You know, if you have two humans that are way different sizes, but one is much bigger than the other, the bigger human is going to give off more heat than the littler human. Something called emissivity, that matters. What in the heck is emissivity? Well, it's worth spending a second on that. Let's say you've got this black shirt, and coming in is a bunch of sunlight. And the black shirt is very good at taking that sunlight and turning it into heat. Everybody's got experience with, black clothes or get warmer. So that means the black shirt has a very high emissivity. Emissivities go from 0 to 1. So something that's really, really, really good at taking this incoming radiant energy, this light, and turning it into heat, that has an emissivity of 1. So what would be something that has an emissivity of close to 0? Something like a mirror. Just the first mirror that came to my mind was this one. Have you ever seen this thing before? My wife and I were wandering around in Chicago. We'd never heard of this thing. We looked over and we're like, oh my gosh, what the heck? It's called the bean. Anyway, if light is coming in toward this thing, it's not very good at taking that light in and turning it into heat. It is very good at just reflecting it outward. So it has an emissivity closer to 0. So for a substance's power that it's giving off, its energy, this is going to not be very good at it, and this is going to be much better at it. And then finally, what else matters? We want the math to work. You guys have experience with Newton's law of universal gravitation. It was like this. It was m1 and m2 over the distance squared. And if we just put in numbers here, we got these crazy big answers that didn't make sense. So we have to use a constant, the big G, to make the math work. Well, this is the same kind of thing. To make this math work, we have a new constant. Okay? And this constant is called the Stefan-Boltzmann constant. Stefan Boltzmann. So the Stefan-Boltzmann constant, I think he has 2 N's on his name. No, it doesn't matter. So now we're actually ready to put together a pretty easy equation. And let me clean this up a little bit. So here we go. The power in watts that something gives off is And the way that you'll usually see it written, here is the Stefan Boltzmann constant, a little baby Greek letter S, like a little sigma. And then you have the emissivity of the material. You have its surface area, and that gets multiplied by the temperature. And experimentally, we've discovered that it's actually proportional. It equals the constant times the emissivity times the area times the temperature to the 4th power. So there are people out there who know exactly, there are probably people out there who know exactly why it's to the 4th power. I am not one of those people. So anyway, here's our equation. Okay, this equation will figure out how much energy anything is giving off. So what kinds of questions could I ask you? I'm probably never going to ask you to solve for this because that's a constant. But I could ask you to solve for something's emissivity, or something's area, or something's temperature. And of course, I would ask you to figure out the power that something was giving off, the wattage. So why don't we solve one of those right away, or right now? So just to show you how easy the problem is, let's say that something has an emissivity of, let's say, 0.85, so it's kind of on the dark side. It's pretty decent at turning incoming radiation into heat. Let's keep its surface area pretty simple. Let's say it has a surface area of 2 square meters. Let's say that its temperature is, just for the heck of it, let's say it's 500 kelvins. And we want to figure out the power. What's its wattage? How much energy is it giving off per second, joules per second? So to solve this problem, we need to know the value of the Stefan Boltzmann constant, and it is 5.67 times 10 to the -8th. And its units, if you care, watts times meters, -2, kelvins, -4. And as you know, I'm not a big stickler for the units, so this is going to be it. That's our constant. So let's solve this. So we're going to have, do I need to even write this down? Yeah, I probably should. So we're going to have 5.67 e to the -8th times the emissivity, which was 0.85, times the surface area, we said it was 2 square meters, times the 500 to the 4th power. So order of operations, we need to do this first. So let's take care of that. So let's go calculator. And how do we do this? Let's go 500 x to the y 4. So there's our temperature to the 4th power, times 2, that was our surface area, times 0.85, that was our emissivity, and times 5.67 times 10 to the -8th. And we get 6,024 watts about. Okay, so if you had an object that was 2 square meters, its emissivity was 0.85, and it was a temperature of 500 kelvins, it would give off 6,024 watts as long as it was at that temperature. So there you go. That is how to figure out the amount of radiant energy given off per second by anything.